Like to.
So I was gonna just advertise something in case this discussion is about like basic bias and variance. In case you have not done a course on Monte Carlo or I guess simulation methods or computations, you can go to this webpage, which is the webpage of the course. It's shared initially. If you click on this link, which is my undergrad course, and there's very nice notes. I'm not saying this because it's my notes. You can judge yourself. There are notes about this basic stuff that you can start from basically exact sampling, so rejection sampling, IID sampling, rejection sampling, and go all the way up to SMC. But that's 140 something pages. This is what I'm trying to do here. So those, but if you want like reading, this is sort of notes here. I have sort of I'll try to publish this at some point. So it's good that some people are reading. Okay, that's undergrad kind of lecture, which would be useful for people who actually may not have much prior knowledge. All right, so let's go on with the discussion. So what we had derived this estimator, which is the basic, I call it basic importance sampling estimator, because again, the reason I called it basic, because I assumed that I was able to evaluate pi, and this function, this weights exactly this, these are the same things, and hence we have seen that actually lets us to get an unbiased estimate. Right? So very simple. Proof, you can take the expectation of the estimator, things cancel, and you get to much for integral. Okay, so you can derive even the variance, which is again, I will not sort of, I guess it's again a simple derivation. If you wanted to compute the variance of this thing, you just sort of go through the computation. Only thing you do here is that you compute the variance of the expectation with respect to Q, because samples are from Q. Of course, a constant in the variance comes out as square, right? This is sort of under the probability rule. And then, of course, because samples are IID, you can sort of push variance inside, and you get this expression. Because you have n times the variance of this product, one n cancels. And then you basically write the definition of the variance, and the variance is given this way, and you get an expression like this. So what is important? A few things are important. You have a 1/n rate for the variance. It is going to decrease as n goes to infinity. This quantity is very interesting because it's actually related to chi-square divergence, which again, I will not go into detail a lot. It's not quite the chi-square divergence as it is because there's a function in it, but you can make manipulations, and this is some sort of distance between the target and the proposal. That's what I'm saying. Actually, as it is some sort of distance between target times the test function and the proposal. So that's sort of distance where it tells you in order to actually have low variance, right? I'm not going to go into detail here, but your target times the test function should be close to Q. So that actually it relates to optimal proposal and all. And here what I'm saying is that formula, if you look into it, will show you that if you have something like this, then this is sort of, this gives you very low variance. Actually, it's possible to make it 0. Yeah. So there's a Q that you can choose. The variance is 0. But let's not go into that discussion. Okay, this is the variance of the basic IS estimate. I'm not going into that discussion because that only applies to the basic IS estimator. As long as we go out of where we can evaluate pi, then the 0 variance becomes a bit impossible. Then discussion will not go out of the window. So, okay, so let's sort of, I guess I should write the other way around, pi proportional to gamma. Let's sort of assume that I don't have access to pi, but I have access to an unnormalized distribution, right? And what do I mean by that? I mean by that is what I mean by that is I have an access to pi, which is written in this form, and normalizing constant, right? So this appears all the times, of course, in practical problems where you sort of want to sample from a posterior distribution, right? Bayesian this posterior distribution, most practical example. In that case, pi would be posterior, and then let me do it anyway. In that case, pi would be posterior, and then you would have your likelihood times your prior and the py, right? And of course, you know the likelihood, that's your model. You know the prior, that's your model. So you know gamma, but typically you don't know the normalizing constant, which is of course part of the entire inference problem. So in order to sample from pi, which is the posterior in this case, you would have to work with an unnormalized version of your target, and you would not have the normalizing constant available. So you have to be able to just use the unnormalized target and solve your integration problem. Right? Let's say you want to integrate against the posterior, one of the things you would want to do. Okay, so with the same trick, but the trick is slightly different in this case, because now I'm going to write the same integral. Now I'm going to write it as ignore q's for now, right? If I integrate pi, and pi is given as gamma over z, and what is z? Z is an integral. Z is an integral of gamma. Normalizing constant, obviously it is an integral. I hope the camera is switching, is not very annoying. Okay, so when I write this, if you ignore q's, of course, the integral with respect to pi would be integral with respect to gamma, normalized by integral of gamma, right? If you ignore the q's, this is what happens here. Integral of phi with respect to gamma and integral of gamma, because that's normalizing constant. So that doesn't change, of course, interact with phi. I mean, for clarity, you can have x primes here. If it confuses you to have the x, these are just dummy variables, right? So I use some x, but okay. I do the same trick now, but for both cases. So instead of just having q here, which was the previous approximation, I do, okay, now I have numerator and denominator. I do the same trick here. So I do identity trick twice. And of course, there was a recent paper and we discussed this with Victor. You could actually, there is no reason you should use the same q here, right? But this is usually how people started doing it. Obviously, I think it's better to use different q's, but for this talk, we will use the most basic approach, it's same q. And once you do that, you basically do the same approach. So now I have a ratio where I can just do Monte Carlo estimators, but for both cases, right? So I can sample from q, approximate that integral. I can sample from q, approximate this integral. In the first case, the test function is sort of replaced by test function with this weight. And now this thing is capital W instead of the lowercase w. This is sort of unnormalized weight, if you would want to call that way. That's usually how it's called. And here is the same thing appears here, the unnormalized weight integrated against q. Okay, so this is sort of the notation, right? I'm just going to replace the ratio with the w. And if you plug the Monte Carlo estimator, so you sample from q n times, and you just plug the Monte Carlo estimators, you get one on the right-hand side. 1 over n's will cancel, so the estimator will no longer have 1 over n in front, as opposed to the usual Monte Carlo and basic IS one. So they cancel, and then you will have this form, right? So you have weighted sum of phi, and normalize with this I equals j. What is that? So j equals 1 to n, right? I equals j. So I wanted to use a different in this here, of course. I could use I, otherwise it gets confusing. So I use j, right? J equals 1 to n. Okay, so this is some sort of normalizing constant, I guess. You can see that. And I can write everything compactly. I can just say, okay, if I define this normalized weight, so each wi, so remember now this w evaluated at xi, I denote it as wi, just simply, in order to just avoid writing this all the time. And I can just group these things together, and I can define a normalized weight this way. And of course, you can see that these are now weights called as like properly called weights because they will sum up to 1 because I normalized them. And the estimator will turn out to be the one that is here. Right? So what's the difference between the previous one? First, we don't have 1 over n as we had in the previous case, because in this case, because of the approximations in both cases, in the ratio, 1 over n cancel. And these weights are normalized properly, right? In the previous case, there was no normalization. Okay, so this is called self-normalized importance sampling, as you can see from the title. If you see SNIS around, this is what the algorithm is. You sample from Q and you compute this estimator, and this is self-normalizing importance sampling estimate. Okay. Question with Haribos, I will give Haribos no points. Is this estimator unbiased? So I can give a hint instead of waiting. So you can see that, do you agree that, for example, this is an unbiased estimator of this? Right? At this point, you agree. And this is an unbiased estimator of this. You agree? Now, what happens to the ratio? What happens to the ratio? So there are two unbiased estimators in the ratio, but then we have a ratio. And guess? Those of you who downloaded the slides. Yes, no, because a ratio of two unbiased estimators, unfortunately, is not an unbiased estimator. Would be very nice, but it's not the case. So this ratio is not unbiased. So what you need to do, and I will not go into the specifically biased derivation. Of course, when you want to do theory about self-normalized importance sampling, you don't start from like, okay, it's unbiased, and what is the variance? You have to essentially also handle the bias, right? Because you have to prove that the bias decreases with a certain rate. And there is this general result about self-normalized importance sampling. And at the end, if I have time, I will try to go into the proofs of this a bit. Probably not on the board as I would like, but probably just on the documents I have here. But there are these general results available just as the Monte Carlo estimator. And so this is a bad bound we discussed with Pierre. Obviously, this is the most simple thing you can do, and better things probably. But if you just assume everything, sort of put heavy assumptions, you just get the same rate as the Monte Carlo rate, with an only sort of slight problem is that this thing should be, I guess, like it can be arbitrarily close to zero, right? It's a fixed number with your, like, given a model, it's a number, obviously, but it can get arbitrarily small, so the bound could be bad. But the good news is, I guess you can handle that with increasing number of particles if you have a plot. Yeah, that's there is something in the bound that says this rate is in some sense the same as the IID rate, Monte Carlo rate, right? So that's the message. Even though you don't have access to pi and so on, you still get the same rate. Okay, so that was a question about this infinity norm. So this infinity norm is nothing but the maximum of the function inside of it. Okay, just think about that. So if phi is a Gaussian, obviously the maximum, I don't know what number Gaussian is a maximum, it's just is a number is bounded, the maximum value it takes, right? So is it for an indicator function, it's just one. If the indicator is just 1 or 0, the maximum of an indicator is 1. Otherwise, it's just maximum of the function. This is why it also doesn't work for the unbounded case. Obviously, if your phi is unbounded, phi is a x, so phi x equals x, then an infinity norm cannot be bounded. In general. Okay, so let's go back to particle filtering. So I had like this sort of rate from filtering, right? We stopped. We stopped with filtering, and we went into this sort of importance sampling. And we had importance sampling. Of course, I just explained things for a general target. You have pi, you want to compute an integral, you take your samples from a proposal and reweight, and then that gives you sort of an estimator and so on. So let's see how this relates to filtering, and if you can use this idea for filtering, and if you do, what happens and how right. So we are back to the standard problem where I have a hidden Markov process that evolves over time. I don't observe that. It is hidden signal process. Observations come conditionally on each xt, and then the tau, to remind you, the notation of, obviously this notation keeps changing, but just to remind you again, the tau is the transition kernel and G is our, right? So this was the focus. Okay. So before we go into details, right? I mean, derivation is going to take you from importance sampling to the filter and so on. I just want to explain the algorithm a bit intuitively, because that algorithm makes intuitive sense in some sense as an evolutionary algorithm, I guess. And then we can go back and actually try to derive why it pops out in the way it does, right? So what is the particle filter algorithm? So there is like 3 steps to it. And I'll go sort of slowly these 3 steps. I'll try to make it intuitive. So maybe I can do it on the board. To explain the algorithm on the board is an interesting idea, but so let's sort of go through the algorithm, because I guess when you implement it, this is the most important thing, that you understand what the algorithm is doing. Otherwise, all right. So you can see the algorithm has 3 steps, right? So it has this prediction step or sampling step, we call it prediction or sampling. So it is drawing from the transition canal given xt minus 1. I'm going to simplify this because I don't want to change like tau t and so on. And there is the computation of weights. And the computation of weights looks like this on the slide. This is proportional to xti. So what is proportional to mean? It means that I compute this for every I and I normalize them, right? So this is basically, in other words, I don't want to use this side. In other words, it's essentially, it means that gyt given xti is normalized with the same quantity, okay, for every I. And then I have resampling. And resampling is done basically a multinomial sampling. So you have weighted set of particles, right? You have weighted set of particles. You have weights attached to them. You sort of sample this weighted set of particles. You sample each one of these particles with respect to probability of each weight. So, you know, the weights sum up to 1, obviously, because we normalize them. So the resampling is essentially you go and look at your particle set. Each has a probability attached to it. These are weights. You sample these particles with respect to this probability. So this is, I guess, a way to get sort of samples that has equal weights. So I call them tilde, I guess. Yes. So tilde, 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 tilde. I'm going to be consistent. Let's go from small x, and then this is tilde, and then this is the normal sum. Okay, so what is the algorithm doing, right? So imagine like the tracking scenario. What is the tracking scenario? Tracking scenario you have, so now tracking, imagine the tracking scenario and my object is here. And I can use color. So I have a tracking scenario and my object is here, right? This is through xt minus 1. Obviously, I don't know this, but I have a Monte Carlo approximation of it. What does it mean? I have particles just approximating this distribution, right? Okay, so this is my Monte Carlo approximation. And after resampling, so imagine resampling was done in the previous iteration, so these do not have weights yet. So these are unweighted samples. Each of them have equal weights. So I know that my system goes like this, right? Let's say tau just drives my system like this. Let's say I know tau correctly, so there is no model mismatch problem. So this would come here. I know that. This is my model. Of course, what makes sense is for me to just move my particles towards that using a transition canal, right? So I want to move all of them to predict where the system is. Of course, my system is stochastic, so the underlying system is also stochastic. So you move your system with those particles. So you move your particles with the system because you think that's what's going to happen to the white dot anyway. And then you get an observation. Let's denote the observation with another color. So you get YT, so single observation. So you observe in 2D something like this. You observe, let's say the observation was here. Now, what you want to do to weight your particles with respect to your likelihood, right? So what is this evaluating this function? For fixed y, it evaluates each particle's likelihood, right? So what does it mean? It means that if this is very close, probably this is a good particle to explain this observation. So this will have higher weight. This will have high weight. Maybe these will have super small weights, right? Because these are far away. And these will have higher weights and so on. And I have some now weighted set of particles. What I want to do is, of course, in order to sort of move ahead and have a better set of particles, I want to kill the ones with low probability, right? Because those are low weights, low probability samples. So I want to do resampling, which replicates maybe these things, maybe this thing twice, maybe this thing 3 times, because it's, you know, I'm resampling with the weights and resampling with replacement, which means that I can get the same sample again. And I practically probably kill these ones. And I will get like these samples. And then, okay, this is my new estimate of YT. And you do the same thing again. You predict, you weight, you resample. Right, so this is the algorithm. Okay, this is sort of the 3-step. So you sample, you have a predicted set of particles, which was the yellow dots. You weight them, so you give them probabilities. You say this is a good one, this is a bad one, and then you resample. So this is why it's an evolutionary algorithm. You can see that because sampling is a bit like mutation. You change you have a bunch of individuals. You change them, they mutate. And then they are evaluated with the environment, right? So G you can think as a fitness function. So G basically decides whether a sample is a good fit or a bad fit. In this context, it is the likelihood, but it can be more general. And then you kill the ones that are low fitness, and then the ones with high fitness, they reproduce. Reproduction means, of course, if you resample its replacement, a particle with high weight will be replaced, right? Probably it's going to be sampled more of this. Okay. So where does the algorithm come from? Okay, so what this slide means is that, okay, this is like, it makes sense, right? I mean, okay, makes sense in one sense. I guess it was derived more or less with this intuition in mind. But why did we go through importance sampling in the first place and then just had a heuristic explanation? So what's the link? Like, what is the? You can see that it resembles an importance sampler. There are weights and they are normalized. And but you know, that's it for now. You can see that much, I guess. But then there is no other relationship. So can we just actually put it in context of importance sampling? And that's the goal. So for this, actually, we will not use the prediction update recursions. So you remember, you may expect that now, in order to filtering, we discussed prediction recursions and update recursions with the Kalman filter. You remember, in the Kalman filter, we realized them in a Gaussian case and they were exact, but otherwise there was this prediction update recursions. But essentially, in order to charge the filter as an important sampler, I guess that's what we want to do. You have to sort of take the view and look at what happens in the path space, not just individual steps, but you have to look to the entire system as one sort of trajectory. So your trajectory of X, I guess, is a one trajectory or one sample. You have to think about distributions over the paths, right? So we will have to look at the path space. Yes, we will instead develop a sampler on the path space. Any questions about the algorithm before I move on to its derivation? Yes, wrong. Yeah.
What is the purpose of the resampling step?
Really good question. Great question, actually. So normally a resampling step is theoretically not necessary, at least the way that sequential importance sampling was derived. But then you have, if you don't do resampling, you have lots of weight degeneracy. So weights over time, they become, we will go into that actually. We will go into that very shortly. Weights become very uneven. Effectively, you get one sample, one weight one, and others are zero, which obviously a bad sampler because you effectively have one sample. That's why it was introduced. I don't know if it's a good motivation. I guess, like, I think it's also, it's seen as an extra error, but I'm not sure if that's the case. But yes, practical reason. We will develop sequential importance sampling, so we'll go into this resampling. Okay. Any other question? So let's do a bit of sort of decompositions in the way that we did for the.
And it's maybe just one short comment. When you're explaining how you assign weights to the particles, YT and XT don't live in the same world. So actually,
yes, in this case, yeah, exactly. So in this case, they don't, yeah. So if in this case, for example, X's are 4-dimensional, right? I mean, yeah, that's good comment. So X's are here 4-dimensional. Well, in this particular specific example that I was also talking about tracking, and then YT is 2-dimensional, right? But of course, when you evaluate GYT XT for each particle, then this gives you a number basically. This is a function from this joint space to R. So they don't live in the same space, but when you evaluate, you get a weight, which means that you have a number here, and then you can normalize them, and it gives you a set of weights, right? Yeah, space. They don't actually give it space, yeah. Right. Okay, let's go into this path recursion, key recursion on path distributions, and we will try to use this for importance sampler. So what we will try to do, we will try to get that algorithm as a particular instance of an importance sampler. If you look at the right level, so we are not going to look at the level of XTs, we are going to look at the level of X0 to T, so the entire path. So let's say my target is this. What is this target? This is the posterior distribution of everything from 0 to T. So remember the Markov model, we have X's and then we have Y's, each come from X's. And we want to get the posterior distribution of x given y1 to t. So this is the distribution I defined. And now I will try to do important sampling on this space for this distribution. Right? Obviously, it's a crazy idea, but you will see that you can actually make simplifications and we will arrive at that algorithm, which is obviously intuitive from another perspective. Okay, how you do that? You just get a joint, you write your joint over the marginal, base rule, joint over the marginal. And then I use my state space model conditional independence. So I can write, this is the joint distribution of everything. Obviously, it's a product of these transition canons and the G's, right? You can write the distribution of all the variables with the conditional independent structure as a product. Of course, because of that product, you can also write up to t-1, you can get that same distribution. And the last variables, you can explicitly write it as tau times G. This is the composition of the conditional independence. And I do the same. Remember, we did a similar trick before. I do the same for normalizing constant. I just get the variables 1 to t-1 and then write the last one. This is true chain rule probability. For all practical purposes we have here. And of course, then the idea is to recognize that this is the posterior of the joint the previous time, t-1, had a typo, t-1 here. So posterior, and then you have a sort of an extra term, right? So what is this? This is basically, you can update the path distribution here over the entire path using the previous path distribution and some sort of operation here, right? So you have to sort of multiply with transition canon and likelihood and divide by the normalizing constant. So like a base update to the whole path somehow. Okay. This is the relationship. And if you wanted to do importance sampling, just start from like, this is just a change of notation. It may look complicated, but if you go back to importance sampling slides, what I'm doing here is exactly the same. It's just that instead of x and y, I'm just writing x0 to t. You know, looks scary, but it's exactly the same. So what if we wanted to do importance sampling? So we can choose a q like that, q0 to t. I am not just choosing q of x. I am also potentially making it dependent on the data. I mean, nobody tells you that you can't use data in your proposals. You can use your data. So in general, the optimal proposal actually is using the data. But let's say it's just denoting the dependence to y, right? Otherwise, it's just a proposal over q0 to t. So you can take any proposal. Well, obviously, any proposal doesn't work, but in theory, any proposal. Now, if you wanted to do importance sampling, what would weights look like? I sample from q of x, and I have to compute these weights. Essentially, the unnormalized, so remember, I had gamma x over qx, right? That was my weights before. Now I'm just writing everything in the state space sort of formulation. And I'm writing gamma over x0 to t, q over x0 to t. So it's just importance sampling. It's just written x instead of x. Okay, so if you get sort of the samples from q, right? So sample from q, you would just get importance sampling estimated like this. Obviously, you have to normalize that. I'm sorry. Imagine that this is a normalized weight, so lowercase w. So get the samples from q, compute your unnormalized weights. This is gamma over q. And you normalize them and you get your path estimate. So it's an important sampler on the path. And obviously it's a very bad idea, but you know, this is theoretically how it would work. Okay, so if you actually do, now this is sort of what we don't want to do. I mean, if you have a state space model and it could have like 10,000 steps, 100,000 steps, we don't want to just sample and then this dimension could grow. Obviously, 4-dimensional is an easy case. It could have much higher dimensions. We don't want to do sampling in this space and then computing weights, obviously hopeless exercise. So obviously we want to use something more clever. Instead of sampling maybe all at once, can we actually do it sequentially, right? Because if you look at that algorithm, all it does is to sample one at a time. So given the xt-1 samples, it samples the xt and it moves on with computing weights and so on. Obviously, this is a very different idea. So can we actually choose the proposal in such a way that we can do this, right? And one way to do it is just use the natural decomposition. Obviously, that again, this there is y1 to t is missing here. So if you have y1 to t here, this is through again chain rule for any proposal. So you just take a decomposition of the proposal, and you can sort of use the recursion around the weights. And this is sort of the key idea how it will go to as simple as that computation. eventually. But if you look at this sort of thing, now I'm not writing y1 to t here, and I'm writing here. It's confusing. Okay, it's not only not here, but otherwise it's here. So you can write the recursion, and you can try to get a recursion on the weights. So what we are trying to do essentially here, we are trying to do the following. Instead of computing the weights all at once, can we get a recursion? So can we write these weights at time t in terms of the weights at time t minus 1? So we can only get away with computing the new term instead of computing the whole path, and just keep updating it. Right? So that's the goal here. So you can do that. You can just use the same idea that actually we used in the Bayes rule, right? So weight is the gamma over q. Remember, now I'm writing in the whole space, and I'm using the exact same decomposition. So this thing decomposes to this and then this, which is the conditional independence. And this will decompose exactly as in the previous case. Again, remember, there is y1 to t here, using the chain rule. So this is nothing but the chain rule. This is true for any proposal. Okay. And then I recognize that this is actually weights of the previous time. And then I have an extra term that has tau times g over q. And then I can write, maybe introduce new notation saying, okay, this is the weights of the previous time. Now the difference is, this is just computed at time t. This is why I denoted the difference. This is not a typo. So this is the weights of the path of the past, and this is the next addition of time t. It still depends on the whole path, which is bad, but it is the addition of time t. Right? You can see, like, maybe you can associate this t with yt, because this is only using observation of yt. Okay. So this is still not good though, because the idea is that we have here, we have to store all this. So imagine how you compute this weight. If you have particles, let's say you computed this weight. And in order to compute this, you still need all the particles here from all the previous run, right? Obviously, that algorithm is not doing that. It's just using t minus 1. And it's just doing that, and that's it. So can we actually do something so that this actually is not a problem? We don't have to look back all the way to time 0. We can just get away with computing, or maybe storing the previous weights, which is convenient for us, right? And the particular idea there is to choose your proposal independent of y. Well, I guess you can put y in it still, but in this particular case, independent of y, and independent of the past. Yeah, so you choose a Markov proposal. So I'm saying that, okay, I'm going to choose a Q that has a Markov structure. Then it decomposes this way. Then the same derivation will take you to somewhere that looks like this. So this is nice. So now I can do importance sampling sequentially. Right? If you look at it, I can do importance sampling sequentially. What I can do, I can start from time 0, compute my W0. And then I can go to time 1. Now compute the weights of 0 to 1 without actually, so use the weights at time 0, and then just compute these things. These are completely sort of, it just depends on yt. And then I can get the weights of time 1. Right? And then I can do a new proposal, draw from proposal, and compute the new weight. So I can do completely recursive computation in terms of the weights. And recursive in the sense that this does not depend on the past. This was a lot of information. Stick too fast. Okay, so the main idea, the main takeaway is that there is a way to decompose the weights so that you can compute them one at a time. It will connect to that algorithm shortly. That algorithm does that, but because of the resampling, we don't track the weights. I'll explain that. Okay. Now, what is the algorithm? Sequentially importance sampling, but the general one, with the general proposal, I guess with the Markov proposal. Let's say you have the weights, I mean, at time 0, you have the weight you sample from qx0, you compute your weights, gamma x0, qx0, and then that's your first weights. Let's say you have these weights available at time t minus 1, and we have to, like, just as in the Bayesian update case, we only looked at all the time from t minus 1 to t. Let's look at how you update your weights from t minus 1 to t. So you have xt minus 1 particles, bunch of particles, like in the particle filter case. You want to propose new particles, and we draw it from Q, okay? as a proposal. And because proposal is Markov, so I don't have to go back and sample everything. I can just condition on the past and sample, and then I have a theoretically a sample from the past, right? But in order to sample that, I don't have to go back. I can just sample the next one, conditioned on xt minus 1, and I'm done. So that's good. So I have just next sample xti's. And then I have to update my weights this way, right? Where does this formula come from? Exactly the previous formula. So in this next slide, you have these available because you computed them at the t minus 1. We are trying to update it to time t. And this you have to compute. So we have the xt minus 1 particles, xt particles we just sampled. So you just compute that term, which is nothing but tau times g over q, as in the previous slides. Okay, so what essentially it becomes a bit similar now. Instead, I'm not sampling from tau, I'm sampling from q. And the weight computation is not exactly just g. You can see now why it's going to become g, but instead of having g, you just sort of compute this sort of tau times g over q kind of weight and not resampling yet, right? So there's just sampling and weighting. That's the algorithm. So you sample and you weight, and you have a weighted set of particles that's supposed to approximate your posterior. So that's actually, you can show that. Right, so what happens essentially is that you get the algorithm in one slide. If you want to see the algorithm in one slide, you just compute, you sample from your proposal. So these are each qi here, so I is here. You compute your new weights, you compute your updated weights. So you compute your new weights, and in order to compute the weights on the whole path, you update your weights with this product, and then you compute the normalized weights, and that's it. You have a normalized weights, set of weights from 1 to n, and normal set of samples. Well, with all path samples, you have the whole path, right? X0 to t and samples of those. This is sequentially important sampling, basically. This finally leads to this empirical measure. Yes, this is what I was trying to say. It has to be 0 to t, or all has to be 1 to t. Both works. 0 to t, they have to be consistent here. So it has to be 0 to t. Right. So what's wrong with this algorithm? Any guesses? We just discussed it. If you look at these expressions, and this is the kind of updating you're doing. Let's be going. What can go wrong if you multiply a lot of numbers? Oh, well, I mean, in the log domain, you sum them, but what can go wrong? Yeah.
Underflow,
Sorry.
underflow, maybe.
Yes. I mean, related, I guess, like it can be a numerical issue for sure. That's one thing. But then even if you can compute them, like exactly, there's still an issue.
All of the weights apart from 1 become small,
Oh, why?
because you're multiplying numbers that are less than 1 and then with each other, with itself.
Well, we do in the log domain, right?
Okay.
And then you can use the tricks, like
Really something.
subtract them, max of the log, and
It's still the case. It doesn't, even if you do it exactly, then yeah, 1 weight with 1.
So we can run this algorithm, right? So let's do something like this. So this is a very toy system, obviously. So what happens? So these are the log weights. So in particle filter, if you see the tutorial, we always compute the log weights. So you never compute these guys because, you know, compute these guys, obviously you compute them because you want to do resampling. Normally you don't need to compute these. You need to compute this in order to have the estimator. Anyway, you compute this not as a numerical tool, as an approximation tool, but this is how it's done. You compute those products in the log domain. So it's a log of something plus log of the new weight. So this is the system. The black one is the true trajectory, red one is the estimator, and Y is the data. So you can see now log weights look pretty even, right? I mean, they don't look really bad, but look at the scale. So it's so big, it is so big that even a small difference here is going to cause a huge difference in terms of the weights because you are actually normalizing them. You are taking exponentials of these guys and normalizing them. So even if this is 100, 201, and the other one is 202, the moment you normalize them, it is going to collapse to 1. Right? So if you look at this picture, it doesn't look bad at all, right? It's all equally weighted. No, it's not equally weighted because all the problem is that you have to still go back to the domain where things are between 0 and 1, and you have to normalize them. The moment you normalize them, you get this. And this is, of course, is a very nicely behaving system, right? I mean, we don't do resampling here. We still track the system more or less because I guess the true system and the particle filter assumes the correct model and things are good. But you still get this sort of behavior where most of the time you have effectively two samples, one sample. And it is much worse. This is a one-dimensional system, so it's much worse in high dimensions. So you have to do something, of course. We have to do. Okay, so right, so this was the sequential importance sampling. Okay, I should have showed this first and then go on. Anyway, this is the algorithm, right? And then the moment the problem is created at this stage, right? So you do this log computations and you normalize them. And that's the problem. And what you just saw was an example of what's called weight degeneracy, right? If you don't take precautions to avoid that, you're going to have a problem like that. So just sampling and weighting essentially is not going to be enough. So look at that algorithm. It samples and weights, but then it does that selection process I was talking about, where you have to sort of eliminate the bad samples. And what happens at the end of the sampling process, you can see, is that I have an equally weighted sample, right? So that actually reads you from that product. I'll show you that in a minute. To resolve this, the usual approach is to introduce resampling steps or do something at this stage, not just keep doing sampling weighting.
Sorry.
Yeah.
Can you explain again why we get this weight? Like, why does it degenerate?
Well, but I gave a numerical explanation.
Yeah. Yeah, I saw the numerics. Yeah, and I understand.
But the scale is
Scale, yeah, okay, sure. But like, why the actual weights? Why does one of those sort of degenerate? Why do just a couple of those go to 1 and the rest go to 0? Like, I don't see it from the algorithm itself.
I mean, if you try to normalize like 3 numbers, even 2 numbers, one is exponential minus 200, another is exponential minus.
Yeah, on the log scale, yeah, but. Like,
Well, that's the reason. I don't know.
that's the reason. Like, from the
Maybe.
You were way to
speaking.
think about, imagine the likelihood function is time homogeneous. And it's an indicator function. What is that? So when you sample the product,
probability.
you ask the process to stay in the set.
Okay.
All of them are
So, yeah.
maybe one.
So is it algorithmic problem, a problem with recursion of multiplying likelihoods over and over again? It will be dominated by one.
So this is how I see it as an engineer, but
I don't think it's going to be numeric, because even if you have exact computation numerically, you still get weight degeneracy.
yeah, it's not a numerical issue. It's the scale issue. Something.
So,
At least that's how I see it.
so this issue would also be worse if your time steps are small. I see.
Yeah, but I don't. Not necessarily.
Sort of going into continuous time.
Not necessarily. I think I mean,
It would be worse on the assumption that the uncertainties remain the same. In reality, if you scale to smaller time set, you'd have less uncertainty. It would be less bad, but it still wouldn't. It wouldn't inherently get better because unless your measurements are more precise.
Would it be fair to say that the part of the deeper issue is that you're trying to match a target distribution that is increasing in dimension. So distances between the proposal and the target as the dimension increases.
yeah, I guess, but I mean, there's a way to circumvent the issue. So if it was the issue, then same would appear in particle filter, right? If that was the only issue.
But the proposal is not super easy to see what it is like once you do a sampling, right? Because it's not anymore your autoregressive.
Yeah, you're right. Yeah. Yes. Yeah, you're right. Yeah, maybe. I have to think a bit. That's a good point. Yeah. Okay. The moment I show the simulation.
Actually, it's a good way of looking at it, because as you proceed with time, you have more and more variables, the dimension increases, and then you can think of this joint distribution to be kind of narrower and narrower, and it's more and more difficult to find good samples that would actually be coming from that distribution.
Yeah. All right, so what can we do, or what people decided to do against this is introducing resampling. Okay, so I will again look at from my own perspective why this helped. Obviously there is all other sort of explanations, there's many explanations that can be given, I think. But what resampling introduces is it does, okay, so we do the same stuff. So we sample from Q, right? And then we normalize the weights. And technically, I mean, you can denote them with WT or W1 to T, I guess, because once we resample, we severe the connection to the past. So what happens? So imagine I am looking at the SIS here, and then I am at this stage, right? And after computing these weights, let's say I mean, because you can mix, right? You can sometimes resample, sometimes you don't have to resample. We're doing a lot of these things. I think Victor will talk about some of the ESS space. You resample sometimes and so on. Let's say I didn't resample. I have these weights, right? And next iteration, when I come here, so if I resample here after that, I essentially set all the weights to 1/n, right? All the weights set to 1/n because I resampled. And then at the end, the next iteration, I have here only 1/n, right? I don't have anything else because I resampled and I got rid of all this dependence. And then I come here and 1/n, I don't even have to care about them because they will cancel here at the end. So in numerics, when you do run particle filter, you never type the 1/n log weight there because they go away in the normalization. So I can just compute these weights, which is exactly what this is, right? So if I introduce resampling here, what I do is I severe the connection with the past in some sense in terms of weights. So instead of these products and log sum of the logs, I can just keep computing the most current weight and compute the normalized version of these and then do resampling again. If I don't do resampling, because sometimes resampling introduces variance because you essentially create new randomness in the algorithm. Of course, the moment you don't do resampling, you have to keep the dependence to the past weight. The moment you do resampling, you can just ignore this in the next iteration, and then you just get the weight computation becomes very simple. But depends on your proposal. In a Markov proposal, very simple. Right? So this is exactly what the algorithm is doing. And then it makes you get rid of those growing logs that I was at least as an engineer talking about, because numerically that's what's creating the issue for me. Here is you basically get this sort of weight computation, and these are just T's, right? At this point, because I resample all the time now at every iteration. That's how I describe the algorithm. These are all T's, not 1 to T. You can technically write 1 to T, but these are all T's, right? And the final approximation would be WT, normalized one, and the whole path, if you want to approximate the whole path. So this is a bad algorithm in terms of smoothing, of course, because it kills the past trajectories. That's another problem. But at this moment, you just compute the weights in a very simple way. Right? We are one step away from particle filter. What is that step? So look at that algorithm and look at this one, and there's one step. Anyone is up for discussion?
The particles.
Yeah. I mean, what am I sampling from there? Oh, I'm sampling from here Q, right? So essentially, particle filter is an important sampler of this type, but you just choose your proposal as your transition kernel. You just say, okay, this is, I mean, okay, if you look at that problem in the tracking case, it makes sense to propose new samples where the system is moving. Although that's not the best thing you can do. There is an optimal proposal expression, not the transition kernel. So there's a different kernel that you can propose that gives you a lower variance. But in this case, let's come back to that later. If you practically plug tau as your Q, then you essentially simplify to this. And that's the part. So you essentially sample from your tau as there, you compute your weights with respect to the likelihood. Why? I mean, why is that the simplification happens? If you look at this expression, tau and Q cancel. So once tau and Q cancel, you are just left with the likelihoods. So you have your likelihoods, and then you compute your weights. Again, these can be just as T, doesn't have a dependent time. Technically, they do, but then you just have your weighted set of particles, and that's your bootstrap particle filter. right? And of course, the very last, after resampling the very last samples you have, you can use it to approximate your expectations, like in Monte Carlo scenario. Or you can use this sort of weighted approximation to approximate your expectations. It's up to you. You usually use the weighted one because it has lower variance empirically, but you use one that's after something. Okay, so what is good about particle filters as well is that, okay, I mean, this is sort of, again, like an important sampling case, not a very optimal theorem. But the idea is that theory extends to this sort of setting, like the Monte Carlo, standard Monte Carlo theory. You have a square root of rate of convergence. It extends in a very similar way to the particle filtering setting. Of course, the proof is much more complicated, and I will not go over. I will not go over on the board because that would take too long, but we can go in the notes and try to look at a bit how the theory is done. But this is sort of the kind of bound you can get for particle filters exactly in the same way. And this shows that basically, you have these basic guarantees as if the particle filtering approximations you get are as if they are Monte Carlo approximations. Of course, in this bound, the bound will be over T, but you can get rid of that by assuming more terms. Okay, so how does it look like? For example, in this case, I don't know if I can. So in this case, you remember the problem that is on the board. Particle filter, of course, just to give you the intuition, I can try to run it. And it sort of gives you this sort of visualizations, right? I mean, you have a bunch of particles, and like black dot is the thing you're trying to track here, and the blue dots are the data. So again, as Peter said, these are technically not living in the same dimension. The underlying system is 4-dimensional, but I'm just plotting the first two. And these are sort of the particles that you can see they are being produced and being killed, and they sort of sometimes deviate from the black dots. And of course, then the proposal handles and proposal samples close to the black dots, and then the particle filter keeps tracking the system. It's a very sort of noisy, not very noisy, but somewhat noisy system. So you can see the particle filter trajectory is not straight. What am I plotting here as red? So the red particles are here. So the particles are here, these simulated ones. The red trajectory is the average particle, right? So I am estimating the red dots. I'm estimating where the red dot is as a mean of my particles. So expected value of my distribution in some sense. Right? This is how it works for the linear case. If I Are there any questions about the algorithm and then I guess the final approximation? Yeah.
There's an error bound with CT. Does CT depend on the dimension?
Yes. Yes, it's a very good question. In very naive cases, yes. In the other cases, typically yes. Implicit though. They usually say, and we had discussions with Nicola a lot about the important sampling is independent dimension. They typically say that, right? But which is not true. Depends on, this is typically the dimension is there, but it's typically implicit. You can do like a very ugly one that if you want an exponential dependence to D, you can assume that your target has independent dimensions, and you can derive a version of this where the CT is exponentially depending on dimension explicitly. But typically it's not explicit there, but in practice, yes. And so it must be there. Yeah. The other thing is in this particular bound, which is a bad bound, but pedagogical one. So you can actually, I can actually explain this to you a bit, and then it would still make sense rather than a very, very complicated bounds. This grows with time. Obviously, it's very bad here because I mean you don't want your error to increase with time. This is an upper bound. As you have seen the simulation, the error doesn't necessarily increase with time. The theory just has a bad way to handle it. There are uniform bounds, so you can get a C there that is not depending on T. But then it typically comes with a compact space assumption. There are open problems, maybe more. Okay, so what does the algorithm look like? If you want to specialize this to Gaussian setting, obviously Gaussian setting, you don't want to run a particle filter, right? I mean, this system is completely tractable. We have seen that. We're just doing experimentation basically here, just to see. And just to give you a concrete sort of algorithm, this is how you would implement it, right? You sample from this linear system n times instead of just computing the mean and covariance as we did in the Kalman filter. Now we sample. And then here you can see that given yt, I have this likelihood, yt given xt, and each particle gets an evaluation with respect to the data point they get. And in this case, again, it's not just closed location, as Petar said, it's also related to velocity disevaluation, right? Intuitively, maybe like closer better, but it's also about the velocity evaluation there. So you get weights with respect to this likelihood, and you get this normalization, and then you resolve. That's practically how it looks like for the linear system. Right, there's another example we really like because it makes nice simulations. The Lorentz 63 system, there even has a video on YouTube of this. So this is sort of the one that is really chaotic, right? Chaotic in the sense that the system is chaotic. Well, I guess like it's a noisy one, so the deterministic version of this system is chaotic. So it can practically chaotic doesn't mean unpredictable. Now I changed my mind about it, but it means that there's a certain amount of time after which, if you start a system from initial conditions that are too close, it stays predictable for some time. That's that. Otherwise, the particle filter wouldn't work. But then they diverge quite substantially. Right? That's what chaos means. But it doesn't mean they diverge instantly, which is why the filters work. Okay, so for example, if you want to visualize this sort of thing, so this is the system, right? And then this is how. Well, I just project this 3-dimensional system. I project every 2 dimensions, right? So this is xy, xz, zy, I think. So these are the cloud of particles, and the black dot is the, I don't know if you can see it, it's usually in the middle of the red dot, so the filter works really well in this case. And this is sort of one example how particle filter works. So what happens in the observations as you look at, as you look at the setting, so there's a 3-dimensional system. I only observe the first dimension, right? So I guess there's a transpose I'm missing here. So I only observe the first dimension. So I get one of the x1t, that's what I observe. And I don't get the other dimension. So my observation is 1-dimensional. It's a sequence of numbers, noisy numbers. And then I have an underlying 3-dimensional system that looks like this. And then the particle filter you can see is going to recover. So I'm showing you this simulation because essentially this is what is in the notebook. So if you manage to run the notebooks in the web page and share, you're not going to see this because in a notebook, you can't get a visualization like this. It just produces thousands of images in the notebook. But you have the code to sort of do that. And get a visualization like this. Okay. Some nice visual examples. Okay, so let's finish with just this part. I'm a bit on the short side now, but let's discuss the marginal likelihood computation because it is going to be relevant towards the end of the week or maybe earlier. People will do parameter estimation again. As I said here, in the Kalman filtering case, we saw that we could compute this quantity quite easily. And but bootstrap filter is a very similar story. You can just get as a byproduct of the filter, you can get a marginal likelihood estimate, right? That's also very good for model selection. You can compute the constant and you can try to rank models if in the Bayesian model selection sort of way. Of course, it's also good to compute the gradient of the marginal likelihood. So what you do is you basically use the same idea. So we have defactorization here like this. And then the factorization is the same as before. So you have the marginal likelihood as a product of these incremental ones, and these incremental ones, you can change here, but these incremental ones, essentially an integral of the likelihood over the predictive, right? And what you get out of this is that, of course, in particle filter, you can get the approximation of this guy, predictive measure, after sampling, right? So if you look at that picture over there, so after I predict means there was a prediction and sampling step. That meant that I went to those yellow points, right? So there was the predictive samples. If I use just those samples to have a Monte Carlo estimate of this density, so if I use those samples to approximate this predictive, which is a sensible thing to do, then you will get, of course, a Monte Carlo estimator of the marginal likelihood. So how do you do this? If you get the samples and put the predictive density like this, so psi here is approximated by P of n or psi of n alternatively, then you get sort of this sort of term. So it's somewhat intuitive term again. Why? Because the incremental marginal likelihood is sort of the average of the unnormalized weights. So these are the unnormalized weights you can see over there. These are the exact same samples. I had tilde there, it's bar here, but these are the same predictive samples. And then you get sort of average of the unnormalized weights, which is your marginal likelihood estimate, predictive marginal likelihood estimation estimator. And you get, if you multiply those, and you can see what the problem with that would be, but if you could do that, then the expression for the full marginal likelihood is a product of all these things. Of course, people do it in the log, but then that creates another issue. But this is the Monte Carlo estimator of the marginal likelihood, and an amazing result. I think or maybe I don't know if it's the first done there. I actually don't know. But this estimate of the particle filter is sort of unbiased, right? This is sort of not obvious at all, and I think the proof requires a bit of work, so I'm not going to do that. But you can show for the particle filter produces approximations, and the expected value under every randomness particle filter generates, right? The expectation is under every particle, every randomness that has been generated in the algorithm. Then this is sort of unbiased. Why is this really nice? Obviously, it's really nice because if you want to do particle MCMC, so if you want to do MCMC, right? MCMC, you typically need, so if you have a theta here and a prior on theta, which I think there's a talk about particle MCMC towards the end of the week, so I'm not going to go, of course, explain that. But if I had a parameter here and I want to infer the parameter with an MCMC scheme, I need this term in my acceptance rate in the MCMC scheme. And of course, particle filter giving me unbiased estimate of that. And then, of course, if you use the pseudo-marginal sort of approach, which basically says that if you replace your likelihoods with noisy ones, but unbiased ones, your MCMC still works. Which means that actually I can do it instead of, I can't compute this in a state space model, but I can do this, compute this with a particle filter. So I can do MCMC using this, which you will see again. Okay, so what is, yes, so a nice exercise if you want to do something tonight instead of drinking. So you can just run a Kalman filter. I told you how to compute the marginal likelihood. Based on the slides. Obviously, you can find it on Wikipedia. There's nice formulas there. And then you can compute this guy, essentially, with a particle filter. And you will have to see, and we did this. Obviously, this works with very small number of steps because the variance just blows up quite fast. But if you do this like 50 or 100 steps with enough number of particles, you will see that actually these numbers match. I mean, you can just verify it together. Mathematics doesn't require verification, but in order to implement these things, it's a nice exercise. You can just sort of see that these are matching each other. Because Kalman filter is one number, and the particle filter will fluctuate around that number every time you run it. So you have to do Monte Carlo simulation. Okay, so there was a smoothing direction from here, but I will take 20 minutes to try to do sort of the bounds I was showing instead of smoothing. I don't know if you have smoothing. I guess. Yes.
That's fine. Both of them.
I think I will go like I kept talking about all those bounds, and I want to just show you. So I will not be able to prove everything, but the document is up there. So I will go over the document with instead of writing everything on the board, and you can maybe have some directions to if you want to study those bounds for some reason. Then you will have some directions to how to look at them, right? So what I think I can do is write this. I don't think Sarah would like this, but it works. Fantastic. Okay. GPR is there, up there. I didn't arrange it. Okay, so I will just run you through this sort of L2 bound, right? And the reason I'm not going on the board because we don't have time, also it takes a lot of time, right? So I was showing you these bounds, right? For example, the first one was this. So I said, if you have IID samples from your target, then you approximate your Monte Carlo, you have Monte Carlo estimator like this. So this is just the usual Monte Carlo estimate. There is no important sampling, nothing. Then I told you that you would get a bound of this sort. For bounded test functions, that's pretty much enough. And how you do this is not very difficult. If you want to sort of see, this is like not like some sort of alien bound, but it's, in this case, it's especially easy, right? So you just write out the definition. So for example, for this case, this is my target integral. So remember, this is an integral. An integral of phi dx. And this is my estimator, as I wrote above in this corner. Okay, so I just write it out. I just write my estimator. This is my estimator, Monte Carlo estimator. And now I write the definition of L2 norm. So I recall that I told you the definition of L2 norm, which was an expectation and square root. So this is what I meant, right? So expectation squared. So it's like MSE, square root of MSE. This is L2 norm, right? So you get L2 norm. And okay, I now can just try to bound the MSE and take the square root, right? Because that's probably easier. So you can write the MSE. And then you just take so you can just make this trick that you can sum this 1 over n I to the 1. Obviously, this doesn't depend on I, so it just means that it is the same number. And I can take 1 over n as a common factor and take it out. So this comes here as 1 over n squared because there's a square. And then I get this term now. Okay, so this term is quite easy to handle actually because it is a zero mean term. If you look at the expression, obviously these xi's are from pi. And if I take the expectation of this quantity, it is going to be zero mean because xi's are from pi. So it's going to end up being same integral as the right-hand side here. And then you would just get zero. So, and then xi's are also independent, right? Because I draw xi's independently from each other. So if you use these two facts, it's quite simple, actually. So if you get here as we did before, so you get 1 over square root of n. And now instead of writing these guys, I'm writing si here. And because they are independent from each other and they are zero mean, you actually have this sort of equality. You imagine taking a square of the sum, you will have the square of the individual numbers, and then you have the cross products, right? Si, sj's, and so on. But those expectation of those are zero because of the fact that while they are independent plus the zero mean. Then you get this number, and then one final thing is to upper bound this in a quite brute force way. In this case, of course, it's a bad thing to do, but if you simply assume that your test function is bounded, so the phi, what L infinity means is this, your test function is uniformly bounded over the space, you can just upper bound that difference quite brutally using triangle inequality like this. Not defending that is a good bound, but you can do that. So if you do that and plug it in there, then you get that. So n times coming from this, and you get this here 4 times pi square. N is all going to cancel. You're going to get 1n and 4 pi square. If you take the square root at the end, because remember, I am dealing with MSE. So if I take the square root, I get the L2 norm, and I get this bound. Now, if you're sleeping. No, good engagement from the room for the people in the recording. Right. So this is sort of simple, right? I mean, it is not a lot of work, but it becomes a lot of work once you get into the case where things are weighted and things are complex. So for example, if you wanted to prove this sort of results for self-normalized importance sampling, and we discussed now self-normalized importance sampling and all the estimators. If you sort of want to prove the bound, then the kind of bound you get like this is like this, which we discussed. I even told you that this was a bad bound because of the term here, which could get arbitrarily small. But if you want to prove something like this, it gets a bit more. I think this is actually, you want to prove particle filters convergent. This is also the step that is sort of, you use this step in particle filters proof anyway. This is the step that is a bit complex. So what you do is you usually use this chain of inequalities, right? So what I do here, I again write my integral and then my weighted estimator. So this estimator is remember, it's the importance sampling estimator like this. it's just the weight. This is the 5 and the 10. And before I go there, I guess I can show this. I can write this integral in this form, which is really helpful. What am I doing? I'm writing this integral because this guy is a gamma x over z, as we discussed before. I can write the integration, merge it with gamma, and I can have normalizing constant here, right? And then I can do the identity trick here. So if I divide here by q and multiply with q, and divide here and multiply with q, I'm going to get w because w is gamma over q. And then I get everything as an integral with respect. Right, so I can rewrite this thing as this, which looks a bit alien, but it is essentially nothing but writing and dividing by q and then reformulating it, right? And of course, this notation of an integral is sort of very convenient to play with these sort of manipulate these expressions, right? If I try to write everything explicitly, it would get very complex. Okay, there is really one step here, and I will probably have to finish with this. And then you guys are very welcome to study particle filter 1 and ask questions. Okay, so what you do in this sort of setting is typically there's a trick of adding and subtracting stuff, and then you go on with that, right? So here I write my estimator, and I write my integral. So this is my integral, and this is my estimator. This is my estimator, and this is my integral. Now I did nothing but using this trick to rewrite it. So I have the estimator this way, and I am writing this with the qn, right? Okay, and then you can sort of add and subtract stuff, right? Then I need to figure out what I am adding and subtracting. So it is wq, sorry, wq. I can subtract this thing and add that later. I made a bit of a mess, but you can. So I am writing this here and adding that, and adding the same thing, and then I have the original minus as this term. Okay, wasn't very good. That's why I didn't do on the blackboard. But I essentially added this term and removed this term. It's just a trick to move on from it, because it is impossible to move on from it, obviously. Once you do that, you can separate terms. So you can get this first term, obviously comes from the first term is easy. They have the same denominator, so you can just write it as one term. And the second term is hard because the second term will have this denominator, right, this one, and the other one has this, which means that I will have to deal with sort of the algebra here. And if you just sort of write that down, you can see that you can sort of get it out this way. So you can write phi w integrated against qn, and you get this sort of ratio here, 1 over qn, 1 over wq, and 1 over wqn. And because we are like under really sort of strict or sort of strong assumptions, I say, you can sort of take this phi out as assuming that phi is bounded, essentially. So you take the infinity norm of it out, and you can sort of try to write this in an explicit way. So you multiply here with this guy, multiply here with this one, and then you can see that this sort of thing will pop out. It's quite basic, this part. And then things cancel here, these ones. Once they cancel, I'm just running you through, not that you would remember all this, but next time you look at it, you will see that it's all simple algebra, right? Everything, only thing that is slightly, you need to be creative or know how to use it is that I subtract and add something, and you need to sort of think about that. But other than that, you just follow the algebra. Okay, so here there is nothing complicated again. At this point, right hand side and left hand side are non-negative numbers, so you can square them, and you can use this sort of inequality. Once you do that, you get just the square of both sides. This is really nothing but the square, and that's it, and 2 in front because of this inequality. Okay, now if I take expectations, something nice is going to happen. Why? Because I know that these are just like Monte Carlo estimators of each other, right? Look, these are IID samples from Q. This is Q. These are IID samples from Q. This is Q. So if I take expectation, this is an MSE of a Monte Carlo estimator, which we know how to bound in the IID case. So if you take the expectation, essentially you get MSE of Monte Carlo estimator here, you get an MSE of Monte Carlo estimator here. You just use the normal bound, right? So this is just an application of the previous bound, this one. That's it. That's really it. You split in this way, and you see that these expectations are actually just plain Monte Carlo estimators because now they are with respect to Q, which I sample IID from. And then you use, in this case, here the test function is slightly different. So you get this upper bound instead of just phi. Here you get phi already here, and you get W's upper bound, obviously. That's what why we had to assume that was bounded. It's bounded. And essentially you end up using, you end up merging these two terms and you end up. Right? So what did I use? I just used one trick to add and subtract something, and then taking expectations and recognizing that these are just plain Monte Carlo estimates of each other, these two terms in the bound. Hence, I can use the earlier proof that was simple. I didn't do a new proof, obviously, here. And then you just get the result out. Right? If I take the square root here now, I'm going to get exactly 2 phi W, this term, and 1 over square root of it. Right? I don't expect you to remember or immediately memorize all this, obviously, but if you were to look at it, then there were two simple ideas and a few watched videos, I guess. Okay, so I guess I'm running out of time. Yeah, so I'm gonna not go step by step over the particle filter, but I will just go over and tell you this is the step that you use that and so on, and then I guess you can see you can use the previous bounds to actually do what I did here. So particle filter is an induction proof, obviously induction proof, because here, as opposed to previous case, which was pi and pi n, here pi t and pi tn. So what you want to do is you want to prove this for every t. Right? So you start at time 0, and then at time 0, everything is good because at time 0, I sample IID from the prior. I have my estimator with respect to prior. I can easily prove this. This is the first bound. This is an IID case. Okay, so I want to do an induction proof. What I want to assume now, okay, I have this for time 0. I assume this for time 1. It's an induction hypothesis. And if I can prove that it is true for time t, then I am done. I prove for every t, right? Obviously, these constants will change. But if I show that this implies that type of bound, then I'm done for all t because I have it for 0. I can just iterate from 0. Okay, so how do you do this in particle filter? You assume that, fine. So as an induction hypothesis, you assume that this bound holds. Now, let's see how you can prove that this holds for t as well. So the main steps are, of course, you have to do the 3 steps as in the board: sampling, weighting. So you prove the bounds after each step and resampling at the end. And what you do is when you do the resampling, when you do the sampling, so you do draw from your proposal and you have this sort of predictor measure. First goal is to prove something like this, right? So what I want to show is if I want sort of pi t minus 1 bound hold, I want to be able to show that for the predictor measures, I have a bound of this type. So predictor measures stay closed as well. So if the filters were closed in some of these cells, then the predictor measures would be closed. And sort of what you do is there's a simple splitting idea here, which you can look into. So if you adopt this notation, which is just saying the predictor measure is an integral of this type, and I wrote the integral over a kernel a bit more compactly than usual. But if you just use a triangle inequality, what I did here, this is nothing but the same expression. I just use this term and do a triangle inequality. So subtract and add this term and use a triangle inequality, okay? And there are 2 problems, bound this term and bound that term. This is going to be sort of easy, but the first one takes a bit of work. So you do the work, basically, and there is the same trick. So you will recognize that conditional on this guy, as these are independent and 0 mean, is essentially the same sort of argument. You get the same sort of expression where the square of SI sums is equal to the sum of the squares because of independence. And you use the same trick of bounding this with 2 upper bound of the function, and you essentially get this sort of bound for the predictor measures, okay? Obviously, I just stepped a bunch of stuff, but it was the similar argument as in the independent case, yeah?
So you are bounding the conditional variance,
No, and then
or
in this case, and then you take the unconditional expectations. So you take the expectations at the end. essentially initially conditional, and then you just get rid of that. Or maybe I'm doing something wrong. could be there. Okay, so and then no, it must be fine. And then in the weighting case, well, sorry, I'm not there yet. It's actually a bit of work for the prediction. So I did just bound the first term here. The simple argument. The second one is a bit annoying. So you have to bound the second thing, which is the transition kernel. Your previous filter passed through the transition kernel and this optimal object, that is the predictive measure. So this is essentially, yeah, you will see what it is basically. It is essentially the weighted sum of transition kernels, this density. And here it's simple. First one takes a bit of work, but I don't remember. But the second one is simple in the sense that this ends up being just a standard Monte Carlo estimate with a different, if you reparameterize your phi, so instead of having this expectation, which we have to bound, this one here, you can write this as a phi bar with respect to this pi t minus 1. If you do that, you actually get this sort of very plain Monte Carlo. Again, this is the same thing. Well, this is induction hypothesis, right? So we assume that this sort of thing is bounded with bounded phi. It was an induction hypothesis. So I don't even have to do anything. Once I rewrite this in this form, I just again use the induction hypothesis and then I get the bound. So you don't do any work here except reparameterizing this. Well, except rewriting this in a very convenient so that you can use the induction hypothesis, right? And then you merge these two bounds and then you get your predictive error bounds. What happened to your constants? You can track them. It increased by 2. Now we're losing. We are losing as we go. And then there are steps of the weighting. So weighting step is nothing but exactly, so it says using a similar argument. Essentially, it is the same argument as in the importance sampling case. You just do the same thing as I went through for the importance sampling. And you can prove essentially this one. It is exactly the same, this sort of argument I did in detail in the first proof of the importance sampling. So you just do the same and you can prove after weighting. So this is the weighted measure. So measure that is, so you have, show again, sort of the sum of weights, the xi, and the weights are coming from the likelihood and so on as usual. You can prove that the weighted measure approximates the filter as well, right? You can stop here. In theory, you have this bound. After doing weighting, you can prove this. Obviously, without even resampling, you can iterate that and you could have the same result. But empirically, we don't get any results, so we have to still deal with resampling. Right, so here is the bound. And obviously, the bad thing about this bound is this GT psi t is not controlled from below, right? I mean, it can get arbitrarily close to 0, and this bound, depending on this number, see, this thing evolves over time. So it's not like one number that you start and maybe it's bad, you can use more particles, but this number can get 0 as time goes to grows, then, you know, I guess it could be arbitrarily bad. Finally, the resampling step. Resampling step is nothing but IID sampling, which is nothing but original argument. I sample IID from pi tilde, and the error between them is equivalent to n. And if I add all the constants that are incurred in every step, sampling, weighting, and resampling, I end up summing all of them somehow, and then I get an EFCT that is less than infinity, slightly less than infinity. As time grows, it grows. Yeah.
When you define the C2T,
Yeah.
Could you go up again? What's the P?
Oh yeah, so that's a typo. So I'm doing here L2. So this was the LP norm. So if you do this for LP, instead of 2, I'm doing which is simple. LP is more complicated because you have to use some complicated inequality to get those bounds I was showing. Then it depends on all P, and then I was keeping the P dependence. That's a typo in this occasion. It shouldn't be there because I'm doing L2, so it doesn't depend on it. Yes, if you do LP, it's a bit more complicated. It's the same proof, actually, but there's some inequality that you need to find out. Okay, I think this is it. And yeah, as I said, these are all online. These notes and slides and some code are online. So if you want to study tonight, then yeah, that should be enough.
Thank you, Danny. So I think lunch should be ready and we have 1 hour until the end. Whatever is that. So thanks.